Let's go over these concepts in chapter 5, which is chemical accounting. I know this might not be your favorite chapter, but it's really important to understand these fundamentals. And we'll do a lot of practice in class, or we did a lot of practice in class, depending on when you're listening to this video. I'm recording it before we actually had class. So let's go through these ideas, and then hopefully from what we do in class and what you hear here, it will help. And then, of course, practicing is always key, all right? So let's bring this up here. So when we're looking at chemical accounting, of course, we're dealing with moles, we're dealing with stoichiometry. So this is, the fundamental ideas here so that one can understand how these chemical reactions work, but they're rooted in our understanding of the atom that we had before this, all right? So starting from first principles, what are these chemical equations that we all love, right? It's just a way for chemists to summarize what's happening in a reaction. So it's basically like a sentence, right? So we're using symbols and formulas, as you can see in my note, to represent what's happening at an atomic level or at a molecular level, depending on what you're dealing with. So when you're looking at this, when you see the little plus sign, that means what's reacting, right? And then the arrow is showing you the direction in which this reaction is headed. And so on one side, right, you have your reactants. Those are the things that are combining or reacting, and whatever happens at the end of the reaction produces the products, right? Since by convention, just like a sentence, every language has their own way of writing sentences, but for us, we read from left to right, and the chemical equation likewise goes from left to right, all right? Then, as you can see here, we have our reactants and our products, but there's other things that are going on here, right? And that's what, I'm going to go through all these different ideas. Something else that one can also show in a chemical equation or in a chemical sentence is the state of the reactants and products, meaning what sort of form is the molecule or atom in, right? So that's designated as a solid, liquid, gas, or even in aqueous solution, you'll see things that say AQ, right? So here you can see two gases combined to make a liquid. So hydrogen and oxygen combined to make water, right? So, and this would be a more perfect form of writing out your chemical equation, right? Now, the important thing to remember here is our law of conservation of mass, right? What you start with in terms of mass is what you have to finish with at the end. So remember, our definition is matter is neither created nor destroyed in a chemical reaction. So that is the operative thing that's happening here when one's looking at these chemical equations, all right? So you've probably at one point encountered the term of balancing your chemical equations, or they have to be stoichiometric, which I'll talk about as well. And the way we do this, and remember, you have to have the same number of atoms of each thing on each side. So, because you can't destroy that. So if you're looking at what we're just looking at discussing, combining hydrogen and oxygen and getting water, right, here over here, right? So you'll look at this and say, well, this isn't balanced, right? Because you've got two of these, two of those, and over here on one of those. And indeed, it's not balanced. Okay, so if one now looks at this, we have to try and figure out how to do this. Now, you can't make something new here, right? So this is why these things, this is hydrogen peroxide, it's not water. So this is a different substance entirely, and here now we're making some extra oxygen atoms, and as you know, these are very reactive. With two extra valence, two free electrons in the outermost shell. So that wouldn't be a happy situation. So this is not balanced correctly. You have to balance with what you're starting with. And if you look here, you've got 2, 2, and here you've got 1. The easiest thing here would be to add a 2 here, right? Because then you'll have 4 And you'll see that it's sort of like multiplication, right? And what do you have to do to this to get that? Well, you multiply it by 2, and then you can just add another 2 here. And it makes it, it's really quite straightforward, all right? So this is the one that's correctly balanced, all right? And these numbers that we put in the front are called coefficients. And they're telling you exactly how many of each of these molecules, we're using the correct stoichiometry, can't speak today, will give you, if you're, the correct amount, all right? Now, so then what we did, of course, in class is that we practiced some, right? And you can see some of those examples in my notes, what we use for practicing. So there's 3 of them there. And if that was a little foggy for you in class, I encourage you to do that, repeat them, right? So that you can look at it and use my notes. And there's going to be more practice in the homework. But basically, if you want to, the best way to do this is sort of when you're doing your chemical accounting, you can literally write how much of each type of atom or element you have on one side of the equation and the same on the other. And when they equal, that means that you've balanced, okay? But you'll see that it's really quite straightforward as you move forward, how many of these coefficients you have to add, right? So if you only have 1 carbon here, you've got 3 over there, the easiest thing to do would be to add a 3 in front of it. And then you've got that, but then you have to look at what you're dealing with in terms of your oxygen. And oxygen is out on its own. So I would leave that to the end to balance, because it's much easier to do something that's out on its own and just add a coefficient to it, okay? And so on. So, and again, practice makes perfect, and that's why I give you guys homework to do this work, okay? Now, the important thing to understand, though, is that atoms have different masses. And just like, if you, this is always a good example, comparing ping pong balls with golf balls, they're about the same size, but we all know that a golf ball is heavier, and that's just because there's more things in it, right? So if you have a kilogram of both of these, you know that you're going to have more of those ping pong balls, right, relatively, because the golf balls are so much heavier, okay? And this makes a lot of sense, but as we were saying before in class, when we first looked at this, and remember Dalton was the one that was talking about how much of each of these elements, they weigh different masses, right? But our first way of looking at this was using reactions combining gases. So it made it difficult to do any chemical accounting, because like we did in lab, if it was an open system, you'd lose that gas. So it got very confusing at first, and it was difficult to understand how this was happening, because you couldn't see gases, right? So understanding how these things take place and how to balance them, well, we started to do that before we actually understood what an atom was, all right? So if you look back, and remember our journey to understanding an atom, it took a long, long time. Even in the early 1900s, we still had trouble understanding this. So if we go back and we did our Gay-Lussac's law, right, the law of combining volumes, they use gases, right? And they were able to determine that certain volumes of gases, when combined, would always produce a certain volume of the product, okay? And obviously we're dealing with gases, so what they said is that they had the same temperature and pressure to weigh these at, or to monitor these at, and this observed idea of combining certain amounts of different gases to get certain amounts of product, that was referred to as the stoichiometry of that reaction, right? And again, keep in mind that they did not yet understand what an atom was, but they could see that these things were combining in certain ways, right? Now, so they knew that there had to be some sort of relationship between these in terms of the substance of what was going in there. Now, Avogadro, when he was looking at this, he suggested, now remember they didn't know yet what an atom looked like or what an atom was, but he suggested that since these would always combine in certain amounts, right, he suggested that equal volumes of gases at the same temperature and pressure, right, must then contain the same number of molecules. Otherwise, it wouldn't work, right? And again, they didn't know what these things were. They just know in terms of atoms. So they didn't know that nitrogen was N2. They didn't know this yet. But they knew that the substance in some way had to correlate. Okay, so but how could we start looking at these? Okay, and that was sort of the idea, and this comes back to you're looking at Avogadro, right? This is his hypothesis, and he knew that there had to be a certain number of these substances in these gases. And they needed some sort of a standard with which to do this with, right? And it wasn't until later that they actually were able to do this in terms of masses and atomic mass units. But Avogadro was given credit for this because he's the one that came up with the idea that there must be the same amount of a substance in an equal volume of this gas, all right? So we already spoke a little bit about Avogadro's number, right? And that is 6.02 times 10 to the 23. Now, I had said to you that this was something that was essentially set by scientists, or by chemists. There had to be some way to standardize reactions so that we could understand how they were working. And just like you need a standard mass in order to figure out how much something weighs so that we're all speaking the same language. Right now, mostly metric, like we were talking about before. But that is something that is arbitrarily decided by groups of humans. So similarly, they had to figure this out in terms of what kind of an atom that we were going to talk about so that we could, or an element, I should say, what kind of an element we were talking about and what the size of the particle was. So there was a lot of discussion and back and forth. Should it be hydrogen? And then oxygen was another idea. But eventually they settled on carbon. And basically everything was decided relative to carbon, carbon being the main unit. And since and it would be 1/12 the size, and that makes sense, right? If you look at the periodic table, why these ones, so 1/12 the size of the proton. And using that as the standard, and everything else was gauged from that, right? So if you look at it, then hydrogen ends up being 1/12 of the size, right? And then you have the effect of the isotopes as well. So it's not quite 1, it's not quite 12, but then you have to look at the contribution from the different isotopes. But basically, like I said, it was based on the carbon atom, so 12 atomic mass units, and that was then determined to be, in terms of grams, 6.02 times 10 to the 23 atoms of carbon. And of course, now we can work with the 12 grams versus the 12 atomic mass units. And this was the standard. And it's important to understand that when you're looking at a mole, it is just a unit of measurement, right? You can have a mole of anything. If you have a mole of pencils, that means that you have 6.02 times 10 to the 23 pencils. And that's all that means. So this Avogadro's constant, or Avogadro's number, was set then as the standard, and it is based on the mass of 1/12 of a carbon atom, okay? And that's just how they decided. Just like they decided that 12 eggs would make a dozen, right? Or a ream of paper, how much that is, or a box of nails. It's always by weight. You don't count the nails in there, right? Or pairs of socks. That's how it was determined, right? And I think this other one I didn't know about, but a gross of pencils is 500 pencils. That's in my notes, okay? So why do we use that? Well, like I had said to you, it's something that we can see. It's something that we can work with, and we don't need to use, if you're dealing with 1 mole, then you're not dealing with 6.02 times 10 to the 23. It's much easier to work with 1, right? Or 2 or 3. So these whole number units, but in the back of our mind, we understand that when we're dealing with that number, that ultimately how much we really are dealing with is 6.02 times 10 to the 23 times whatever that number is, okay? So how much is that? Well, if you have 6.02 times 10 to the 23 baseballs, that would be about the mass of the Earth, or in terms of drops of water, the mass of the oceans. So it's an incredibly large number. And it's such a large number, it's very difficult for us to imagine it, okay? And this also works for molecules, right? So if you're talking about the mass, or the atomic mass, the formula mass is the same thing. So, or the formula or the molecular mass would be the sum of all the masses represented in that formula. So in my notes, you can see what it is for sodium chloride or table salt. So if you have 1 mole of sodium chloride, you actually have 1 mole of each of those sodium and chloride in there. And you can find out exactly how much 1 mole of sodium chloride is going to weigh, right? And if you weigh it out, that's what you're dealing with. Okay. Same thing with carbon dioxide. That's also in my notes. So you can see that, and hopefully that makes sense to you, and that's important that it does. All right. And then we did this whole thing with dietary intake in class. You know, how much is our daily amount of sodium? All right. So I'll catch up with my slides here. So remember, formula mass is the average mass of the formula. Again, it's going to be relative to that carbon atom. All right. So the atomic mass and the molecular mass, or the formula mass. Okay. The other way of looking at it is percent composition. And that, when one's looking at that, you look at the percent of the whole, right? So we also did a little bit of that in class. So if you're looking at how much, what percentage of that would be sodium, if you're looking at sodium chloride, you can also figure that out, right? So 1 mole of sodium chloride is 58.44 grams. And in that, you know how much sodium is, and then you can find out what percentage of that is equal to sodium, all right? And then by you can infer then what it would be for chloride, all right? So here as an example, potassium permanganate, you can see that you can look at the periodic table and look at the mass of potassium, manganese, and oxygen, and you can figure out how much, relatively speaking, you have of each of those in your molecule, right? And like I said, that's when it comes really important to, in practice, your daily intake levels, right? So how much you should take in during a day, right? So if you look that up, it works out to be about 2.4 grams, or 2,400 milligrams. And then you can look at how much that is. And that would be from your textbook example on page 145. And essentially, all you need in terms of your dietary intake of sodium, which we usually get from salt, we talked about this in class, would be basically a teaspoon. That's all you need. We get in a lot more, but that's really all we need, right? And then, of course, these videos are to help you go over this. They go through some more examples, just like we did in class. But it's really important to me that you are able to understand how this works, all right? And then, of course, our mole lab demo. So we did more of it, practically doing it in class, because mostly in lab, our stuff is already set up for us. So you don't actually have to do these solutions, but it's important that you understand where this comes from, okay? Now, oh yeah, there was our mole lab demo. So how do you do this? Mass over the moles over the molar mass. All right, so there's your relationship. So remember again that this was mostly figured out at first looking at gases, and they didn't say, I didn't tell you what volume was, but basically 1 mole of any gas would occupy at standard temperature and pressure, so 0 degrees centigrade and sea level pressure, so 1 atm, and that would be 22.4 liters. So that would be a volume. So we could think of it in that way, okay? And then when you're dealing with that, if you've got 22.4 liters, you're dealing with exactly 1 mole of that gas, okay? So that's how that that is standardized. Okay, so now let's go back to our idea of looking at our chemical equations. So when we are balancing these chemical equations and we're looking at our atoms, okay, it's very difficult to imagine, you know, one atom of carbon and one atom of, or one molecule of oxygen reacting. We can't see that. And what I'm hoping you've gathered now is that when we're dealing with it at, you know, atom or molecule levels, we're actually dealing the same ratio when we're dealing with moles. And this is why it works when we can actually figure out how much of these need to combine, because you're not going to be able to weigh out 12 atomic mass units of carbon, but you can weigh out 12 grams of carbon. And that's the really important aspect of this, right? So these coefficients in chemical equations actually represent the number of moles, all right? Now, if we carry that a little bit further, okay, this also applies to mass relationships, okay? So now we're dealing with our stoichiometry. We've got moles, but remember, whatever you start with, you have to finish with, okay? So you can't get more of something at the end of your reaction. You have the total mass of what you're starting with has to be the same mass of what you're ending with. So you can still use your mole relationships to figure out and work with masses, okay? So if you think of it this way, just say you wanted to make sure that at the end of your reaction you had a certain amount of a product, okay? Then you would know exactly how much of your starting materials you would need in order to obtain that. Right? And this is really important when you're in industry, you're in business, and you're trying to come up with the right formula to get what you need, and then you have enough product to then sell, because you don't want to make too much, because then you're not going to get money for that, for example. And then if you don't have enough, your customer is not going to be satisfied with you. So you could think of it in that sort of perspective as well. Okay, so these ratios of your reactants and products can be used to determine how much in mass you're going to require to get the desired amount of product. Okay, and this is really important, of course, when we're talking about green chemistry, because you want to reduce waste. Okay, now when it comes to green chemistry, what they're actually using is something called the atomeconomy, all right? So when I was going through chemistry, we had to do this thing in the bottom. We always calculated our percent yield. So how much we anticipated we were going to get, so our theoretical yield as a factor of our experimental yield, how much we actually got, and then we would times that by 100%. Because the important thing to understand is that when you're dealing with these reactions, they're not perfect practically. In the lab, things happen, okay? So it's not a perfect world. You're going to get some loss, all right? So like I said, when I was going through chemistry, I had a course, analytical chemistry, and this is what I did for a whole year. We were obsessed with our year, meaning school year, obsessed with our percent yield, and we would use our percent yield to figure out what our starting materials were based upon theoretical yield, and the product that we would get, the higher my grade, basically, is how it worked. And that was sort of the old way of looking at this, because we were only thinking about the product that we actually wanted. All right, but the greener way of looking at this is looking at the total atom economy, because it's not, if you look at percent yield, notice there's no, you're just dealing with the product, or the product that you're most interested in. You're not worrying about the waste or the side products that are being produced as a result of trying to get to your final reactant. Okay, so when you're dealing with the full atom economy, and we're going to look at these examples again, you get the mass of your desired product, but you're also now considering everything you put into the reaction to get that desired product. So here's your masses of all the things that you came in. in with, right? So this is considering any reactant, including the byproducts of the reaction, are considered now in this calculation to find out really how good is my chemistry, because there can be more than one way to arrive at a product, okay? And that's what we're talking about now in terms of green chemistry. So we went through this example in class from your textbook, right? Making butene, all right? And there's two different ways to arrive at butene. If you want to look back on my notes, which you have on Blackboard, so that's page 10, right? So if you look at it, the first way to make butene, right, combining methyl bromide with sodium hydroxide, you definitely get your butene, but your efficiency is only, or not your efficiency, your atom economy is only 31.7%, right? Whereas if you do it a different way, okay, as you can see in the lower one, okay, combining C4H6 with hydrogen gas, all right, you're actually getting a 100% atom economy, which is a much greener way of going about this. All right, so that's sort of what we're dealing with, and basically you're just splitting that C4, or you're hydrogenating, I should say. You're hydrogenating, or so bubbling through hydrogen, your previous reaction, and then you're getting what you wanted, right? So you're actually starting with butane, and you're getting butene, and that's sort of what is the idea here. Okay, so the second one is a greener way of doing it. Okay, now, so if you look here, your atom economy, all right, you're looking at the total amount of your useful product over the masses of all the reactants, and then you find out what you get in terms of your yield, all right? So in this case, making ammonia, right, combining nitrogen and hydrogen, and you have 100% atom economy, all right, in terms of this one. But on the other hand, if you're going to combine here and look at your useful product, but notice here now you're having a waste product of carbon dioxide, all right? And now your atom economy is only 56% because you're now considering this, all right? So you're not just looking at your useful product, okay? So that's sort of the important difference here. So understanding, you know, a green solution versus a just, you know, getting what you want kind of solution to your problem of getting what you desire to sell as your product, for example. Okay. Now, then at the end here was just an idea of solutions, things that we deal with in lab. So, you know, the amount of solute in a given amount of solvent, right? So remember, the solute is the thing dissolving, the solvent is that which is being dissolved. It is referred to as how concentrated the solution is. So if it's a dilute solution, that means it's a relatively small amounts of a solute in a solvent. Concentrated would be the reverse, right? A large amount in there, okay? And way of expressing this, there's three different ways to express this. You can express it as molarity, and this is the one that we deal with in the lab all the time. So the number of moles of that substance in a liter of solution. And that is the typical way of doing it. But if you go into the lab, there's certain things that you can also use. So percent concentration, that is quite standard as well. So percent by volume. So that would be the volume of the solute in the as part of the volume of the whole solution times 100. Okay, so sometimes you'll see like a 5% solution of sodium chloride, for example. That is another way of doing it, or percent by mass. So the mass of the solute in the mass of the solution. That's another way of doing it. So if you take that hydrochloric acid that we're dealing with in lab, we're expressing it in molarity, but if you look at the jug of hydrochloric acid, I've got a picture of it here, it's actually sold as a 38% mass solution of hydrochloric acid in water. So it's not just pure HCl, it's actually a reagent grade. So how much is actually, it's actually aqueous. So, but that's what we're dealing with in terms of what you're actually using. And when we do the calculation, we factor that in there in order to arrive at our final solution. All right, just so you know. Okay, so that covers all of the different ideas that we're thinking about in this chapter. And hopefully that going over this again with you is helpful, but definitely make sure you practice these different ideas so that you are familiar with them, and you'll see more practice in the homework. All right, and this is probably the most difficult our math is going to get, but it's really fundamentally important that you understand how some of these things work, just as I expressed here, you know, in terms of green chemistry. So understanding amounts and the stoichiometry of a reaction and what you're getting and how much you want and how much waste. All of these are very practical things that we have to deal with when we're dealing with making almost any kind of substance out in society. All right. Okay. So thank you. And hopefully that helps.